Welcome to the Crypto Bootloader training series. In part 3, we'll discuss the Crypto Bootloader flow and implementation. The following are the steps involved in the creation of a secure firmware image with Crypto Bootloader. Step 1. The product manufacturer creates a new firmware image in a trusted environment. Step 2. The product manufacturer encrypts the image and creates an authentication tag making use of AES-CCM. During this step, metadata, such as the firmware version, is also included during packet creation. Step 3. The encrypted firmware image is sent to the device in the field. Step 4. The firmware image is received by the device in the field through the bootloader communication interface. Step 5. The firmware image is decrypted and its authenticity is verified. Here, the same key used to encrypt the firmware image and create the authentication tag is used to decrypt and verify it. Step 6. If the firmware image passes the verification checks and the firmware version is newer than the one currently stored in the device, the new firmware image will be written into memory, making use of the bootloader memory modification functions. This slide shows in more detail how the encrypted firmware image is created. The following input parameters are given. 1. Path to the firmware image. 2. Firmware version number. 3. Symmetric authenticated encryption key. 4. Initialization vector. For the authenticated encryption algorithm shown, AES-CCM, it must be a number that will never be repeated for a given key. Since the number must be used only once, it is typically known as a nonce. Software tools will take these parameters and process the firmware image. The first step is the firmware preparation, in which the firmware image is split into chunks. Chunks represent small segments of data or code to be stored sequentially in a given address location. Chunks contain two fields, address and data. The next step is packet preparation, where metadata is prepended to each chunk. This metadata includes the firmware version, the packet number, and the total number of packets. The last step is applying authenticated encryption. A symmetric key along with an IV nonce are used to generate a tag for verification and to encrypt the packet. This is done making use of the NIST recommended authenticated encryption algorithm, AES-CCM, counter with CBS-MAC. On the microcontroller side, the encrypted firmware image is received by the bootloader communication interface. The same cryptographic key used to perform authenticated encryption on the product manufacturer side is now used to decrypt and authenticate the data. As mentioned earlier, the algorithm used is AES-CCM, which is based on two cryptographic primitives, AES-CTR, counter mode, for encryption, and CBS-MAC, cipher block chaining message authentication code, for integrity and authenticity verification. It is important to note that the flow shown in this slide is a simplified representation and does not include all the steps involved in the actual AES-CCM algorithm. Each packet will first be decrypted. The MAC algorithm will then generate a tag of the resulting plaintext data. The computed tag and the tag received along the firmware image are then compared. If the tags match, the firmware will be loaded into memory by the bootloader. If they don't, an error message will be sent. Bootloader memory functions perform additional checks on the metadata prepended to each packet. These checks make sure the firmware version is newer than the one currently being used and ensure that the complete firmware image was received. One important aspect when dealing with symmetric cryptography is how the keys will be stored and how they can be updated. Crypto Bootloader makes use of a key structure which contains metadata, such as the key type and the key version. The key type is used to distinguish between the different types of cryptographic keys used by Crypto Bootloader. AE key is the key used for authentication and encryption, while a key encryption key is used to encrypt key material, which can be an AE key or a newer KE key. The key version is used to prevent downgrading attacks. Once a key has been disabled and is no longer in use, this mechanism protects the Crypto Bootloader from loading it again. Keys are encrypted, making use of AES-CCM as well. An IV nonce and a KE key, along with the key key type, and key version, are fed into a tool to generate the encrypted packet used to update the key. This packet preparation happens in a trusted environment on the product manufacturer's facilities.